Hey guys, and welcome back to another video. In this video, we will be talking about exponential functions. Alright, so to begin with, let's talk about the general form of an exponential function. Right, so any exponential function can be written in the form f of x equals a times b to the x. Okay, and a quick way to see if a function is exponential or not is to see if the input value, in this case x, is in the exponent. Okay, but here a is known as the initial value and b is known as the base. Okay, and then there are some restrictions on a and b though. So for a cannot equal 0, right? Because if a is equal to 0, then this whole thing goes to 0, and then it's no longer exponential. Okay, and then for b, the restriction is that b has to be greater than 0, and b cannot equal 1. And the reason being for this is that if b is less than 0, then you have a negative number raised to an exponent. And if this exponent is odd, then it's going to keep changing signs. So it's going to on the graph, it's going to fluctuate like that. And that's not exponential, right? So that's why b has to be greater than 0. And b can't equal 1 because if b is equal to 1, then this would become a times 1 to the x. But 1 to the x is just 1, so this just becomes a. And then you're just left with a constant function. So if that's why we have to have these restrictions, because otherwise it won't be an exponential function. All right. And then there's two main types of exponential functions. We have exponential growth, and we'll have exponential decay. So for exponential growth, the graph looks something like this. And for exponential decay, it looks like this, right? So for growth, notice how that as x approaches infinity, the function is also approaching infinity, right? So essentially, as x increases without bound, the function is also increasing without bound. And then, however, when x approaches negative infinity, then it seems as if the function is approaching some value. And indeed it is. So in this case, it's approaching 0. But exponential functions always have asymptotes. So in this case, it will have a horizontal asymptote at y equals 0. Okay, and all exponential functions have horizontal asymptotes. Now over here, the end behavior for this function, so as x increases without bound, it approaches the horizontal asymptote, which in this case is just 0. But if it was like y equals 1, let's just say, then it would approach that value. It would approach a 1. And then as x decreases without bound, this is going to diverge to negative infinity. It's going to do so slowly, correct, because it keeps going up, but it is going to diverge to negative infinity. Okay? So that's basically the end behaviors. Also, growth happens when b is greater than 1. So when your base is bigger than 1, that's when you have growth. And then decay is when b is between 0 and 1. All right? And one last thing to note is that notice how exponential functions are 1-to-1, right? For every input value, there's exactly one output value. So that's just a good thing to keep in mind. All right, now let's do some practice problems. All right, so let's see. So let's say we have f of x equals 2 times d to the x. G of x equals, let's see, 2 times 1 over 5 to the x, and h of x is equal to a fourth times 2/3 to the x, right? So pause this video and see if you can figure out whether each one is exponential growth or decay. All right, so now let's see how we do this. So for this first one, we have to look at the b value, right? So in this case, b is equal to 3, which is greater than 1. And so we know that exponential growth happens when b is greater than 1. So that means that this is just exponential growth. Okay? This one, b is equal to 1/5. And that's less than 1, so it's between 1 and 0. And that means that it has to be decay, right? And then for this one, same thing, b is equal to 2/3. And that's between 0 and 1. So that means it has to be decay. So as you can see, it's pretty easy stuff. All right, so now let's talk about the natural base. So natural base. So this is just f of x is equal to e to the x. So first of all, what even is e? So it's like a special number, right? So it's kind of like pi. So like pi is equal to 3.14159 and so on. E is a similar special number. So e is equal to like 2.7181, and that's all I know. But it's like a special number like pi. And it's called Euler's number because it was named after the mathematician Leonard Euler. But the reason that you have to know this function is because it's super useful in mathematics to like model stuff. So like it could be modeled, it could use to model like continuously compounded interest. You can also use it to model like population growth and like half-life, like radioactive decay, right? So it's just like the general idea is like it could be used to model a bunch of stuff. And like as you progress in your math classes, many of the exponential functions you're going to deal with are going to have e as the base, especially in like calculus and other higher level classes. But yeah, so and actually the formula for continuously compounded interest is p is equal, or a is equal to p e to the rt, right? So notice how we have e as the base and then some variables in the exponent. So actually, let's kind of use this equation to solve some problems. So I'll write it again up here. So continuously compounded interest, the formula is a equals pe to the rt, right? So like some problems you could solve with this is like, for example, let's say you have like $3,000 and that you deposit into a bank. So you deposit $3,000 in the bank, and then it pays, the bank gives you like 3% interest, but it's compounded like continuously, right? So like there's like every second, like every millisecond, it's compounding 3%. Okay, and so then they might ask you like, how much money will you have in 7 years? So how much money in 7 years? So you can use this formula, right? So A is like your final amount, so that's what you want to find. P is like your initial amount that you deposited, so in this case 3,000. E is just like a number, and R is the interest rate, so 3%, so 0.03, and then T is just the time in years, so 7 years. All right, and then we could just like put this into a calculator or something, but you would end up getting like 3701.03, right? So like if it like if you put this money into a bank and it compounded continuously, you would get that much money. Whereas like, and I did the calculation for this on the side, if this like was only compounded, let's say like quarterly, right? So like, let's say it was only compounded quarterly, then you would only have like 3,698.44. So like just by compounding from quarterly to like continuously, you made like a lot more money, right? All right, good. So let's see some other applications of exponential functions. So let's say we have potassium 42, right? And they give us the half-life of this. So half-life of potassium 42 is 12.36 hours. All right. And then you start with 500 milligrams of potassium 42, and they're asking how much is left after 24 hours. All right. So first of all, what even is half-life? So basically, this is saying that it takes 12.36 hours for a sample of potassium 42 to half, right? So like for example, if we have 500 milligrams of potassium 42, then after 12.36 hours, we can expect to only have 250 milligrams left, right? And that's just because potassium 42 decomposes. So they want us to find it after 24 hours. So the general equation is the following. So this basically represents A naught is like the initial amount that you're starting with. So in this case, it's 500 milligrams. And then 1/2, that's because it's half-life, right? And then T is just your variable, so it's after 24 hours. And then H naught is your half-life, so 12.36 hours. So 24 over 12.36. And if you were to put this into a calculator, you would get 130.150 milligrams left. Right? Alright. Alright, so let's see, let's do like one more example, one more application of exponential functions. It's population growth, right? So let's see, they give us that, let's say like the population of some country is, so population is equal to 15 million, right? So let's say population of some country is equal to 15 million, and they tell you that every 30 years it doubles. So every 30 years population doubles. And they want you to find the population in 2024. And just so you know, this population was in 2004. So 2004 population was that much, and they want the population in 2024. So clearly that's like 20 years, right? So the general equation for population growth is P naught is equal to P is equal to P naught, and then times 2 to the power of T over D. So this is basically representing like the time it takes for the population to double. So that's what D is, right? And they tell us that 30 years the population doubles. P naught is our initial population, so 15 million. And then we want the population after 20 years. And the time it takes to double is 30 years. So if you put this into your calculator, you should get like 23.811 mil. So after in like 20 years, in 2024, population of this country would be 23.811 million. Assuming that this rate would continue, right? Because sometimes it 30 years to double, but that's not exact, right? That's just like an estimate, it's like an approximation. All right. But yeah, that's pretty much it for exponential functions. If you found this video helpful, please make sure to leave a like and please make sure to subscribe. Other than that, I'll see you guys in the next video.